About 250 million years ago, Earth wasn't struggling, it was thriving, a single giant supercontinent stretched across the globe. On land, powerful predators ruled with almost no rivals. Plant eaters pushed through long dry seasons and scarce water. In the ancient oceans, creatures from ancient families swam on, families that had already survived every disaster the planet had ever thrown at them. Life had found a perfect rhythm, a balance that had lasted for millions of years. Nothing hinted that it was all about to end. Then the rules broke. Not slowly, not in one corner of the world. In a shockingly short window of time, entire ecosystems vanished from the fossil record. Nearly 90% of all life in the seas disappeared. More than two-thirds of the animals on land were gone. Even the strongest, the creatures that had dominated for ages, were suddenly wiped out. The toughest weren't spared. In some cases, they were among the first to vanish. This wasn't a story of the weak falling first. This was something far bigger, a total collapse of the world that had worked so perfectly for so long. Tonight, we're stepping back into that late Permian world at the very height of its power, right before Earth's most devastating extinction event. We're going to walk among the systems and the deadliest monsters that once ruled this planet. If you love these journeys into Earth's dramatic deep past, do me a favor right now. Hit the like button, subscribe, and drop a comment telling me where you're watching from tonight. That way, you'll never miss the next incredible chapter we uncover. Now, let's travel back in time and discover what this ancient world was really like. The continents had gathered into a single immense body of land, drawn together over ages until no wide ocean separated their edges. This vast union, known as Pangaea, stretched from pole to pole, its interior so expansive that distance itself became a defining force of life. Along its outer margins, the seas still breathed against the land, but far within, the memory of ocean influence faded into something distant and almost forgotten. Across these inner regions, the land opened into enormous deserts, not the shifting dunes of a single horizon, but dry expanses that extended beyond sight in every direction. Moisture rarely reached these interiors. Winds carried little relief, and clouds passed overhead without release. The ground baked beneath a relentless sun, then cooled sharply when darkness returned. Day and night held a quiet tension, each bringing its own extremes, shaping the rhythm of survival. Seasons deepened this contrast. Without nearby oceans to soften the air, temperatures swung with a wider reach. Heat pressed heavily during long summers, drying soils and thinning water sources. When colder periods arrived, the same land that had burned now hardened under chill conditions. Life here did not move easily between comfort and hardship. It endured, adjusting slowly to a pattern that offered little stability. Closer to the edges of this supercontinent, the world shifted in tone. Coastal regions received the moderating presence of surrounding seas. Moisture traveled inland from these boundaries, allowing vegetation to take hold more consistently. Rivers formed more reliably, carving pathways that connected land to ocean. These outer zones became places where ecosystems could spread with greater density, where plants and animals found conditions that were less severe, though never entirely gentle. The limited length of coastline played a quiet but powerful role. With so much land fused together, the proportion of shore compared to interior was far smaller than in later ages. Habitable zones clustered near these edges, while the center remained vast and difficult. This imbalance created a world where life was unevenly distributed, where abundance and scarcity existed side by side but rarely overlapped. Creatures that lived within this arrangement adapted in ways that reflected their surroundings. In the dry heartlands, survival favored those that could conserve water, that could endure long stretches without relief or retreat beneath the surface when conditions grew too harsh. Along the margins, where resources were more dependable, different strategies emerged. Movement between regions became a challenge, shaped not only by distance, but by the shifting demands of climate and terrain. Geography did more than define where life could exist. It influenced how life behaved, how it grew, and how it competed. Barriers were not always mountains or rivers, but vast stretches of inhospitable land that separated populations over time. Isolation encouraged variation, subtle at first, then more pronounced as generations passed under differing pressures. In this unified world, everything was connected, yet not equally shared. The shape of the land dictated pathways and limits, guiding the flow of life across its surface. What thrived near the edges could not easily cross into the interior, and what endured in the center carried traits shaped by constant challenge. The supercontinent stood as a quiet architect, its scale and structure setting the conditions long before any sudden change arrived. Heat did not settle gently over this world. It gathered, lingered, and pressed downward with a steady persistence, shaping the surface of the land and the behavior of everything that lived upon it. The global climate of this time carried a warmth that extended far beyond what is familiar today, not as brief intervals of intensity, but as a long sustained condition that rarely loosened its hold. Sunlight arrived with little resistance. Across much of the supercontinent, skies remained clear for extended stretches, allowing solar energy to reach the ground uninterrupted. The result was a landscape that absorbed and held this heat, releasing it slowly through the night, though never enough to restore true balance. In many regions, warmth became the constant backdrop against which all life unfolded, not an event, but a state of being. Rainfall, when it came, was uneven and often scarce. Vast areas received little precipitation across long cycles of time, leaving soils dry and vegetation sparse. Water did not move freely across the land, and where it did appear, it became a focal point around which life quietly gathered. Outside these limited zones, dryness shaped the rhythm of survival, influencing how organisms grew, fed, and endured. Near the outer margins of the landmass, the pattern shifted. Here, the presence of surrounding seas introduced a different dynamic, one guided by the slow breathing of seasonal winds. Monsoon systems formed as temperature contrasts between land and water drove the movement of moist air inland. These winds carried clouds that released heavy rains, sometimes in sudden and powerful bursts, transforming the edges of the continent into places of temporary abundance. This cycle was not gentle or predictable in a comforting way. Wet periods could arrive with intensity, saturating the ground and filling waterways, only to withdraw again, leaving behind drying soils and shrinking resources. The alternation between moisture and aridity created a landscape in motion where stability was always temporary and adaptation required flexibility. Beneath these patterns, subtle shifts were already unfolding. Climate did not remain fixed even within its broader extremes. Periods of relative stability were interrupted by fluctuations that altered temperature, precipitation, and atmospheric composition. These changes did not announce themselves loudly, yet their influence could be traced in the gradual adjustments of ecosystems, in the distribution of species, and in the quiet retreat or expansion of certain forms of life. Organisms that thrived here carried within them the imprint of these conditions. Adaptations emerged not as sudden innovations, but as careful responses shaped over generations. Some developed ways to conserve moisture, reducing loss through skin or respiration. Others adjusted their activity to cooler periods, moving under the cover of night or seeking shelter during the most intense heat. Growth cycles aligned with the availability of water, and reproduction followed rhythms dictated by shifting environmental cues. Even in regions touched by seasonal rains, resilience remained essential. The abundance brought by monsoons was never permanent, and life that depended on it had to endure the intervals between. Roots reached deeper, behaviors shifted subtly, and physiological limits were tested again and again against the demands of a climate that offered little consistency. In this world, extremes were not anomalies. They formed the foundation upon which ecosystems were built. Heat, dryness, sudden rains, and gradual shifts all intertwined, creating an environment that required constant adjustment. Life did not simply exist within these conditions. It was shaped by them, refined through them, and carried forward by its ability to endure what rarely softened. The air itself carried a different balance, subtle in appearance yet deeply influential in every quiet breath taken across the land and sea. It moved as it always had, invisible and constant, but its composition had shifted over long spans of time, altering the way energy flowed through living bodies. What filled the lungs of this world was not quite the same mixture that would later define more familiar ages. Oxygen, the element that fuels movement and growth, existed in lower abundance than in certain earlier periods. It still supported complex life, yet it offered less ease. Each inhalation delivered a slightly reduced share of what muscles and tissues required, and over generations, this difference shaped the limits of activity and endurance. Creatures did not collapse under this constraint, but they lived within it, adjusting their pace and form in response. Alongside this, carbon dioxide lingered in higher concentrations, woven into the atmosphere as part of a broader greenhouse effect that sustained the warmth already settled across the planet. This gas, though less directly felt by individual organisms, influenced the global system as a whole, helping to retain heat and maintain the elevated temperatures that defined the era. The air became not only a medium for breathing, but a quiet regulator of climate. Within these conditions, metabolism followed a different rhythm. The rate at which organisms could convert oxygen into usable energy was gently restricted, encouraging efficiencies rather than excess. Movement favored bursts rather than prolonged exertion, and behaviors often aligned with conserving strength. Over time, bodies adapted to make the most of what was available, refining internal processes to operate within narrower margins. Size, too, was influenced by this atmospheric balance. In environments where oxygen is more abundant, larger body forms can be supported with greater ease, as tissues receive ample supply to sustain their demands. Here, with slightly reduced levels, growth encountered natural boundaries. Many species remained within moderate ranges, their proportions reflecting a compromise between strength, energy needs, and the capacity of the air to sustain them. Breathing itself, though never a conscious effort, carried a subtle weight. The exchange of gases within lungs or lung-like structures required a bit more from each cycle. Some organisms developed more efficient respiratory systems, increasing the surface area through which oxygen could pass into the bloodstream. Others adjusted their behavior, avoiding sustained exertion during the warmest periods, when oxygen availability felt even more limited. In aquatic environments, these dynamics extended further. Water holds less dissolved oxygen than air, and as temperatures rise, that capacity diminishes even more. Marine organisms faced a layered challenge, navigating not only the chemistry of their surroundings, but also the thermal conditions that influenced it. Subtle shifts in oxygen levels within water could shape where life gathered, how it moved, and how densely populations could form. The atmosphere, though rarely noticed directly, became a quiet architect of possibility. It defined the boundaries within which life could operate, guiding evolution through constraints that were steady rather than sudden. Adaptation did not arise from a single moment of pressure, but from countless small adjustments made over generations, each one refining the relationship between organism and air. In this balance of gases, invisible yet ever present, the conditions of existence were set. Every breath, every movement, every growth carried the imprint of an atmosphere that offered just enough and no more. Long before the first true dinosaurs would leave their mark, another lineage had already taken hold across the land, shaping ecosystems with a quiet authority that would endure for millions of years. These were the synapsids, a group whose presence defined this era so completely that the rhythms of life itself seemed to move in step with them. They did not resemble the creatures that would come later, nor did they fully mirror those that had come before. Their forms carried a blend of older reptile-like traits and emerging features that hinted at something new. Within their skulls, a single opening behind each eye allowed for stronger muscle attachment, giving rise to more powerful bites. This structural detail, subtle at first glance, marked a significant shift in how these animals fed and interacted with their surroundings. Across varied landscapes, synapsids occupied roles that extended through entire food webs. Some moved as large herbivores, shaping vegetation patterns through constant feeding, while others became skilled predators, tracking and capturing prey with increasing efficiency. Their dominance was not sudden or abrupt, but the result of gradual adaptation refined over generations that responded to the demands of their environment. Their posture began to change as well. Earlier land vertebrates often held their limbs splayed outward, their bodies carried low to the ground in a posture that limited endurance and speed. Synapsids showed a subtle reorganization of this structure. Their limbs angled more beneath the body, supporting a stance that allowed for more sustained movement. This shift did not transform them into swift runners by later standards, but it introduced a new range of mobility, a quieter efficiency in how they crossed the land. Within their mouths, another transformation unfolded. Teeth were no longer uniform in shape and function. Instead, differentiation appeared, with some teeth suited for slicing, others for gripping, and still others for processing plant material. This variety allowed synapsids to exploit a broader range of food sources, refining their diets in ways that earlier animals could not. Feeding became a more precise interaction with the environment, guided by specialized tools rather than general ones. Beneath these visible traits, deeper changes were taking place. Their physiology hinted at a more active internal system, one that may have supported higher metabolic rates compared to earlier reptiles. While not yet matching the sustained energy levels of later mammals, these developments suggested a gradual movement toward more complex regulation of body processes, a quiet preparation for what would eventually emerge. Their success was reflected in their diversity. Across the supercontinent, different groups of synapsids adapted to local conditions, filling ecological roles that ranged from small, burrowing forms to large, dominant herbivores and formidable predators. Each variation carried the imprint of its surroundings, shaped by climate, geography, and competition, yet all remained connected through shared anatomical features. In this era, they were not transitional figures awaiting replacement. They were the defining presence of terrestrial life, the architects of ecosystems that had reached a delicate balance. Their interactions, from feeding to movement to reproduction, wove together the structure of the world around them. What makes them especially significant is not only their dominance, but their legacy. Within their lineage lay the early roots of traits that would later characterize mammals. The changes unfolding in their bodies, gradual and unhurried, formed the foundation of a path that would continue far beyond this moment in deep time. For now, they existed fully within their own age, shaped by it and shaping it in return, carrying within them the quiet beginnings of a future not yet realized. A tall silhouette rises above the low horizon, its outline defined by a curved sail that catches the light long before the body beneath it becomes clear. This is Dimetrodon, a creature whose presence seems almost sculpted by the conditions of its time, both familiar and distant in form, yet firmly rooted in a world far older than the age of dinosaurs. Its body moves with a deliberate steadiness, supported by limbs that hold it slightly elevated from the ground, though not fully beneath it. The posture suggests strength rather than speed, a design built for controlled movement rather than pursuit across long distances. Each step carries weight, pressing into the earth with quiet authority as it navigates its territory. The sail along its back draws immediate attention, formed by elongated spines rising from the vertebrae and connected by a thin web of tissue. It stands like a vertical surface, catching sunlight as the animal turns. This structure likely served as a tool for thermoregulation, allowing Dimetrodon to absorb heat when temperatures were lower and release it when warmth became excessive. In an environment where conditions could shift between cooler mornings and hotter afternoons, such a feature offered a subtle advantage, helping to stabilize internal processes. Beneath this striking feature, the head tells another story. The skull is broad and equipped with a set of sharp, differentiated teeth, each shaped for a specific purpose. Some are long and pointed, designed to pierce and hold, while others are more blade-like, capable of slicing through flesh with efficiency. This arrangement reflects a predator adapted for processing its prey with precision, reducing the effort required to consume each meal. Dimetrodon did not rely on speed alone to secure its position. Its strength lay in a combination of patience, power, and timing. It likely occupied areas where prey would pass through, conserving energy until the moment of action arrived. When it struck, the force of its jaws and the arrangement of its teeth allowed it to subdue animals that shared its environment, reinforcing its role as a dominant predator. Despite its appearance, it does not belong among the dinosaurs. It existed long before they would emerge, part of a lineage that branched in a different direction. Its classification among synapsids places it closer, in distant relation, to the line that would eventually lead to mammals. This connection is not immediately visible in its outward form, yet it is carried within the structure of its skull and the arrangement of its muscles. Its dominance was not defined by constant motion, but by presence. Other animals within its range would have moved with an awareness shaped by its existence, adjusting their behavior to avoid becoming part of its diet. This influence extended beyond individual encounters, subtly shaping the flow of life around it. In still moments, the sail stands quiet against the sky, a surface that records the passage of light and shadow. The body beneath it remains steady, conserving energy, existing in balance with the conditions that shaped it. Power, in this form, is not expressed through constant activity, but through the ability to endure, to wait, and to act with precision when the moment arrives. Within its time, Dimetrodon embodies a kind of authority that arises naturally from adaptation, a reflection of the world that formed it and the role it came to occupy. Movement becomes quieter here, less defined by weight and more by intent, as if the land itself has learned to carry shadows that think and act with purpose. Among these forms are the gorgonopsians, a lineage of predators whose design reflects a refinement of hunting rather than a reliance on sheer force. Their presence does not announce itself through size alone, but through precision, speed, and control. Their bodies are built for motion that flows rather than presses. Limbs extend more directly beneath them than in earlier forms, allowing for strides that cover ground with efficiency. There is a balance between strength and lightness, a structure that supports bursts of acceleration without sacrificing stability. When they move, it is not with constant urgency, but with an awareness of timing, conserving energy until it can be used with purpose. The head carries their most defining feature. From the upper jaw extend elongated canine teeth, curved and sharpened, forming the characteristic saber shape. These teeth are not simply for display. They are tools shaped for a specific function, designed to penetrate deeply and slice through soft tissue with minimal resistance. Around them, smaller teeth assist in gripping and guiding, creating a coordinated system that turns a single bite into a decisive action. Unlike predators that rely on crushing force, gorgonopsians appear adapted for a more targeted approach. Their jaws open wide, allowing those elongated canines to be positioned with accuracy. Once embedded, the motion that follows is controlled, drawing the teeth through flesh in a manner that maximizes damage while minimizing effort. This efficiency reduces the need for prolonged struggle, aligning with a strategy that favors quick resolution over extended conflict. Their senses likely played a significant role in this method of hunting. The positioning of their eyes suggests forward vision, providing depth perception that would aid in judging distance during pursuit or ambush. Combined with a body capable of swift movement, this allowed them to close gaps rapidly, bridging the space between hunter and prey in moments that left little room for escape. Within their environment, they occupied the highest levels of the food chain. Few other animals could challenge them directly, and this absence of significant threats shaped their behavior. Dominance did not require constant display. It existed as a quiet certainty, maintained through capability rather than confrontation. Other creatures adjusted their movements and habits in response, creating patterns of avoidance that reinforced the gorgonopsians' position. As conditions shifted across the land, these predators remained among the most successful of their time. Their combination of agility, specialized dentition, and efficient hunting strategies allowed them to adapt within a range of circumstances. They were not bound to a single method or environment, but carried a versatility that supported their continued dominance. Their role extended beyond individual hunts. By regulating populations of herbivores and other animals, they influenced the balance of ecosystems, maintaining a structure that depended on both presence and restraint. Each successful capture fed not only the predator, but contributed to a broader equilibrium that connected countless forms of life. In their design, there is a sense of refinement, as though evolution had shaped them toward a focused purpose. They are not the largest, nor the most heavily built, yet their effectiveness places them at the peak. Power, in this form, is expressed through precision, through the ability to act at the right moment with tools perfectly suited to the task. They move through their world with a quiet confidence, carrying within them the culmination of traits that define an apex hunter. Not all power in this world moved with teeth or speed. Much of it stood quietly among sparse vegetation, shaping the land through steady, continuous feeding. These were the herbivores, the great consumers of plant life, whose presence formed the foundation upon which entire ecosystems depended. Without them, the balance held by predators and prey would begin to unravel, their role as essential as it was often unassuming. Across the terrain, Large-bodied plant eaters moved with deliberate rhythm, their forms built to process tough, fibrous vegetation that could endure the demanding conditions around them. Among these were the parasaurs, heavy creatures with broad bodies and thick limbs that supported their weight with stability. Their skin may have carried bony plates or textured surfaces, offering a measure of protection, though their primary strength lay in size and resilience rather than speed. Their heads were relatively small compared to their bodies, equipped with teeth suited for grinding plant material. Feeding was a constant activity, as the energy gained from vegetation required sustained effort to maintain such mass. They moved slowly through their environment, cropping low-growing plants and shaping the distribution of vegetation as they went. In doing so, they influenced not only their own survival, but the availability of food for others. Alongside them lived the Dicenodonts, a diverse group of herbivores that displayed a different approach to feeding. Their jaws ended in a beak-like structure, well suited for clipping plant matter with precision. Many species bore a pair of tusks projecting from the upper jaw, whose exact function may have varied between display, defense, or interaction within their own kind. Their bodies were often more compact than those of parasaurs, allowing for a range of sizes and ecological roles. Dicenodonts adapted in ways that reflected flexibility. Some species appear to have been capable of burrowing, retreating beneath the surface to escape harsh surface conditions. Others moved across open ground, feeding on whatever vegetation was available, adjusting their diet as needed. This versatility allowed them to occupy environments where more specialized feeders might struggle. Together, these herbivores formed a living network that supported higher levels of the food chain. By consuming plants and converting that energy into body mass, they became the link between primary production and predation. Their abundance, distribution, and health directly influenced the success of the predators that depended on them. When herbivore populations thrived, the entire system found stability. When they declined, the effects rippled outward. Their adaptations reveal a deep connection to the conditions of their time: thick skin, efficient digestion, and behaviors that reduced exposure to environmental stress all contributed to their survival. Water conservation became critical, as did the ability to process vegetation that might be dry or limited in nutritional value. Feeding strategies were shaped not by abundance, but by persistence. Despite their size, they were not immune to danger. Predators watched and waited, selecting moments when vulnerability appeared. Young individuals faced the greatest risk, their smaller bodies offering less protection. Even so, the sheer presence of large herbivores created a form of stability, their numbers buffering the system against sudden change. Their movement across the land left subtle marks: pathways formed by repeated travel, vegetation altered by constant grazing. These traces, though easily overlooked, were part of a larger pattern that connected soil, plant, and animal into a single, continuous process. In their quiet endurance, these herbivores sustained the world around them, carrying the energy of the land upward through the intricate layers of life. At the margins where land meets water, a different rhythm unfolds, one guided not by distance or scale, but by the quiet presence of moisture. These narrow zones, where rivers bend and lakes settle into the landscape, hold a kind of continuity that the surrounding terrain cannot always sustain. Here, life gathers with a subtle urgency, drawn by the simple necessity of water. Amphibians remain closely tied to these places, their bodies shaped by a reliance that cannot be easily set aside. Their skin, permeable and sensitive, allows for the exchange of gases and moisture, binding them to environments where dryness does not linger for long. They move between water and land, but never far from the sources that sustain them. Each movement carries an awareness of distance, a silent measure of how far they can go before returning. Along riverbanks, the ground softens, marked by tracks that appear and fade with the passage of time. Here, amphibians rest, feed, and reproduce, their life cycles intertwined with the presence of standing or flowing water. Eggs are laid in these sheltered areas, where they remain protected within a thin boundary between vulnerability and survival. The young emerge into a world that still belongs to water, gradually shifting as they grow, yet never fully leaving it behind. Lakes offer a similar refuge, though their stillness creates a different pattern. The edges become zones of layered activity, where plants root themselves in saturated soil, and small creatures find shelter among stems and submerged debris. Amphibians move through these spaces with quiet familiarity, navigating an environment that supports their needs in ways the open land cannot. Yet, even here, stability is never guaranteed. Seasonal changes alter the extent and reliability of these water sources. Periods of reduced rainfall cause rivers to narrow and lakes to recede, exposing ground that was once submerged. The edges shift inward, compressing the space available for life. Amphibians respond by adjusting their behavior, seeking deeper pools, or retreating into damp refuges that preserve what little moisture remains. This contraction draws other animals toward the same limited areas. As water becomes scarce, its presence defines the movement of entire communities. Herbivores approach to drink, leaving traces of their passage along the softened ground. With them come predators, their attention focused not on the water itself, but on those who must return to it. These meeting points become places of quiet tension, where survival depends on timing and awareness. Amphibians exist within this convergence, navigating a world where their dependence places them at the center of a shifting network. They must balance the need to remain close to water with the risks that such proximity brings. Movement becomes measured, often aligned with cooler periods or concealed by vegetation, reducing exposure while still meeting the demands of their physiology. Their presence also supports other forms of life. As both predator and prey, they occupy an intermediate position within the broader system, feeding on smaller organisms while providing sustenance for larger ones. Their abundance, when conditions allow, contributes to the flow of energy through these concentrated ecosystems, linking water to land in a continuous exchange. In these boundary spaces, life is shaped by proximity and limitation. The edge is not merely a line, but a living zone where dependence and opportunity exist together, held in balance by the presence of water and the quiet forces that govern its reach. Green does not blanket this world in a continuous expanse, but appears in measured patches, rising where conditions allow and thinning where they do not. Forests take shape as quiet clusters rather than endless canopies, their presence defined by resilience rather than abundance. These are the Permian forests, composed of plants that have adjusted to a land where moisture is never guaranteed and survival depends on careful balance. Conifers stand among the most prominent of these trees, their forms reaching upward with narrow leaves that reduce water loss. Their structure reflects efficiency, each needle-like surface designed to conserve rather than expend. Resin flows within them, a protective substance that seals wounds and guards against environmental stress. They do not grow in haste, but in steady increments, building height and strength over long spans of time. Interwoven with them are seed ferns, plants that carry the appearance of familiar fronds, yet reproduce through seeds rather than spores. This adaptation allows them to spread without reliance on constant moisture, a significant advantage in landscapes where water may retreat for extended periods. Their leaves catch light in layered arrangements, forming partial shade beneath them, creating small pockets where other forms of life can persist. Ginkgos add another dimension to this forested environment, their distinctive fan shaped leaves capturing sunlight in a broad, open surface. They are neither dense nor sparse, existing in a balance that reflects their adaptability. Their structure allows them to withstand variations in temperature and moisture, holding their place within the shifting conditions that define the land. These forests differ from the dense, waterlogged ecosystems of earlier times. The towering swamp forests that once dominated have given way to more open arrangements, where space exists between trees and the ground is often visible beneath the canopy. Light filters through with greater ease, reaching the surface and supporting a mix of smaller plants that occupy the understory. The result is a landscape that feels both structured and open, shaped by limitation as much as by growth. Distribution across the supercontinent remains uneven. Forests gather more readily in regions where moisture arrives with some regularity, often closer to areas influenced by seasonal patterns. Elsewhere, they appear in isolated stands, separated by stretches of land where conditions do not support sustained growth. This patchwork creates variation in the environment, influencing where animals move and where they find shelter. Within these wooded areas, stability emerges in subtle ways. Roots anchor soil that might otherwise shift or erode, holding the surface together through cycles of change. Fallen leaves and plant matter accumulate, breaking down slowly and returning nutrients to the ground. This quiet process supports the continuation of growth, allowing the forest to maintain itself even under challenging conditions. Animals interact with these environments in ways that reflect their needs. Herbivores move through the spaces between trees, feeding on available vegetation and shaping its distribution. Smaller creatures find shelter among roots and fallen debris, using the structure of the forest as protection from exposure. The forest does not exist apart from these interactions, but is shaped by them over time. Each tree, each cluster of growth, contributes to a broader system that connects soil, air, and living forms into a continuous exchange. The forest moderates its surroundings, offering shade, retaining moisture, and creating microenvironments where life can persist with greater consistency. In their quiet endurance, these forests form a stabilizing presence within a world defined by variation, holding together the delicate patterns that allow ecosystems to continue. Beneath the larger movements that shape the land, a quieter layer of life unfolds in constant motion, small in scale, yet vast in number. Insects move through this world in ways that often go unnoticed, their presence woven into nearly every surface, every plant, every fragment of organic matter. They do not dominate through size or strength, but through abundance and persistence, forming a living network that supports everything above them. Their diversity appears in countless forms, each adapted to a specific role within the environment. Some move across the ground, navigating through soil and leaf litter, while others take to the air, their wings carrying them between patches of vegetation. Early beetles emerge among these groups, their hardened outer shells offering protection as they burrow, feed, and reproduce. Their bodies are compact and resilient, suited to a life that often unfolds in close contact with the ground. Alongside them, insects with elongated bodies and delicate wings move through the air in slow, steady patterns. These dragonfly-like forms drift above open spaces, their flight controlled and precise. They hunt smaller organisms, contributing to the balance of populations that might otherwise grow unchecked. Their presence adds another layer to the system, linking air, land, and water through their movements. Insects serve as pollinators, transferring reproductive material between plants as they feed or travel. Though the vegetation of this time differs from later flowering systems, similar interactions still occur, with insects aiding in the continuation of plant life. Their movements, repeated countless times, support the spread and stability of plant populations across the landscape. They also act as decomposers, breaking down organic material that would otherwise accumulate. Fallen plant matter, discarded remains, and other forms of debris are gradually reduced through their activity. This process returns nutrients to the soil, making them available once again for new growth. Without this constant recycling, the system would begin to slow, its resources locked away rather than renewed. Their role extends further into the structure of food chains. Many larger animals depend on insects as a source of energy, consuming them directly or relying on other creatures that do. In this way, insects form the base of a complex network, supporting layers of life that build upon their abundance. Their small size does not diminish their importance. Instead, it allows them to exist in vast numbers, ensuring that their influence remains steady. Adaptation appears in subtle variations among them. Some develop protective coverings, others rely on camouflage, blending into their surroundings with quiet precision. Their life cycles may unfold quickly, allowing populations to adjust rapidly to changing conditions. This flexibility contributes to their resilience, enabling them to persist even as the environment shifts. Despite their constant activity, they rarely draw attention in the way larger animals do. Their movements are often too small, too numerous, to follow individually. Yet their collective presence shapes the environment in ways that are both immediate and enduring. They exist as the unseen foundation, maintaining the processes that allow other forms of life to continue. In their quiet, continuous work, insects sustain the balance of the world, carrying out tasks that hold ecosystems together without ever rising into prominence. Far from the shifting patterns of land, the oceans stretch outward in a continuity that has endured through ages far older than the landscapes above. Their depths hold a memory that reaches back through immense spans of time, carrying ecosystems that have developed slowly, layer by layer, with a steadiness that land has rarely matched. Here, life has found ways to persist through cycles of change, building complexity in a realm that remains vast and interconnected. Beneath the surface, marine environments unfold in gradients of light and depth. In the shallower regions, sunlight filters through the water, supporting a wide range of organisms that depend on its energy. These zones become centers of activity, where life gathers in dense formations, each species occupying a place within a carefully balanced system. The clarity and warmth of these waters allow for growth that spreads outward, creating structures and communities that sustain countless forms. Coral reefs rise within these shallow seas, forming intricate frameworks built over generations. Though different in composition from later reefs, they serve a similar purpose, providing shelter, feeding grounds, and surfaces upon which other organisms can attach. These reef systems become hubs of biodiversity, where interactions between species occur in constant motion, each contributing to the stability of the whole. Among these communities, brachiopods anchor themselves to the seafloor, their shells opening and closing as they filter nutrients from the surrounding water. Their forms appear simple, yet they are part of a lineage that has persisted across vast stretches of geological time. Nearby, trilobites move along the substrate, their segmented bodies navigating the contours of the ocean floor. They feed, burrow, and interact within this environment, continuing a presence that has already endured for millions of years. Fish and other marine animals move through the open water above, forming another layer within this system. Their movements connect different parts of the ocean, linking shallow regions to deeper zones. Some remain close to the reef structures, while others venture farther, navigating currents that carry nutrients and organisms across wide distances. This constant exchange maintains the flow of energy throughout the marine world. The oceans hold the majority of life during this period, far surpassing the diversity found on land. Their stability, relative to the more variable conditions above, allows ecosystems to develop with fewer interruptions. Changes do occur, but they often unfold gradually, giving organisms time to adjust and adapt. This continuity supports a richness that builds over time, creating networks of interaction that extend across entire basins. Water itself acts as a buffer, moderating temperature and distributing nutrients in ways that smooth out extremes. This does not eliminate challenges, but it creates an environment where fluctuations are less abrupt. Life here evolves within a framework that favors persistence, where long-established groups continue to thrive alongside newer forms. In these ancient seas, every layer is connected, from the smallest drifting organisms to the larger creatures that move through open water. Each plays a role in maintaining the balance that has developed over ages. The ocean becomes not just a setting for life, but a system that sustains itself through countless interactions, each one contributing to a continuity that feels both steady and expansive. Within this vastness, life gathers, grows, and endures, held together by the quiet stability of the marine world. Out in the open water, beyond the shelter of reef structures and the slower movements along the sea floor, a different kind of presence moves with quiet certainty. Shapes pass through the blue expanse with fluid precision, their bodies designed not for stillness, but for continuous motion. These are the apex predators of the sea, creatures whose forms have been refined over immense spans of time, shaped by the demands of hunting in a vast and unobstructed world. Their bodies are built around efficiency. Long, streamlined profiles reduce resistance as they move through water, allowing them to glide with minimal effort or surge forward when needed. Fins extend with purpose, guiding direction and maintaining balance, while powerful tails provide the force that drives them ahead. Every movement is measured, conserving energy until it must be spent, then releasing it in controlled bursts that close distance with remarkable speed. Among these predators are early sharks, already displaying many of the features that will define their lineage far into the future. Their skeletons, composed of flexible cartilage rather than dense bone, grant them a combination of strength and lightness. This structure allows for swift turns and sustained motion, enabling them to navigate the open water with ease. Rows of teeth line their jaws, arranged in a way that ensures constant replacement, maintaining a sharp edge for capturing and processing prey. Alongside them swim large, predatory fish, each adapted to similar roles through different evolutionary paths. Their jaws vary in shape and strength, some designed for gripping, others for slicing, yet all serve the same purpose of securing nourishment within an environment where opportunities must be taken quickly. Their senses extend beyond simple sight, detecting subtle vibrations and changes in the water that reveal the presence of other organisms nearby. In the open sea, where hiding places are limited, hunting relies on awareness and timing. These predators patrol wide areas, moving through layers of water where prey may gather, They do not wander aimlessly. Their paths are shaped by currents, by the distribution of smaller creatures, and by patterns that have formed over generations. When they encounter potential prey, their movements shift, becoming more focused, more deliberate, as they prepare to act. The moment of pursuit is often brief. Acceleration replaces stillness, and the distance between hunter and prey closes rapidly. Success depends not on prolonged chase, but on precision, on the ability to anticipate and respond within a narrow window. When the attempt succeeds, energy flows upward through the system, sustaining the predator and reinforcing its place within the broader network of life. Their dominance is not maintained through conflict with one another as much as through the absence of true challengers. Few creatures can match their combination of speed, strength, and sensory awareness. This allows them to occupy the highest levels of the marine food chain with a stability that reflects long periods of evolutionary refinement. Over hundreds of millions of years, these forms have been shaped into effective hunters, their designs tested and adjusted through countless interactions within the ocean. What remains is a balance between motion and restraint, between the need to hunt and the need to conserve. In the open water, they move without interruption, part of a system that depends on their presence as much as it depends on those they pursue. Structures rise from the sea floor in quiet layers, built not in a single moment, but through countless small contributions, each one adding to a living architecture that holds entire communities within its form. These reef systems stand as intricate frameworks, their surfaces covered with life that settles, grows, and interlocks over time, creating spaces where thousands of species find shelter and sustenance. Within these formations, density replaces distance. Organisms occupy nearly every available surface, attaching, crawling, filtering, or drifting within the narrow spaces between structures. Each small opening becomes a place of interaction, where currents bring nutrients and carry away waste, sustaining a constant exchange that supports the entire system. Life here does not spread outward in isolation, but gathers closely, forming a network where each presence influences another. The reef acts as a center of biodiversity, drawing in species from surrounding waters and providing conditions that allow them to persist. Small invertebrates anchor themselves along hard surfaces, while mobile creatures move between openings, feeding, hiding, and reproducing within this layered environment. Larger animals pass through or remain nearby, connected to the reef through the availability of food and protection it offers. Balance within these systems is maintained through a delicate alignment of factors. Water temperature, chemical composition, and the flow of currents all contribute to the stability that reefs require. Even slight variations in these conditions can ripple through the system, affecting growth rates, reproductive cycles, and the interactions between species. Unlike broader ocean regions, where changes may disperse over large distances, the reef concentrates these effects, making them more immediate and more visible. The organisms that build and sustain these structures depend on a narrow range of conditions. Their growth is closely tied to the chemistry of the surrounding water, particularly the availability of compounds that allow them to form hard skeletons or supportive frameworks. When these conditions remain stable, the reef continues to expand, adding new layers to its foundation. When they shift, even slightly, this process can slow or weaken, altering the structure over time. Because of this sensitivity, reef systems often reflect changes in the environment earlier than other marine habitats. Subtle increases in temperature or shifts in water chemistry can disrupt the balance that supports their growth. Some organisms may struggle to maintain their structures, while others may find it harder to reproduce or compete. These adjustments, though gradual, signal a change that extends beyond the reef itself. The effects do not remain contained. As the reef begins to shift, the many species that depend on it must respond. Some may move to other areas, while others attempt to adapt within the changing conditions. The density that once supported a wide range of life may begin to thin, altering the interactions that once defined the system. Yet, even in these moments, the reef continues to function as a living structure, responding to its environment with a quiet resilience. It does not collapse suddenly, but adjusts layer by layer as conditions evolve. Each change leaves a trace within its form, a record of the surrounding waters and the forces that shape them. In these complex systems, the connection between life and environment becomes especially clear. The reef exists as both a product of its conditions and an indicator of their stability, reflecting shifts that may not yet be visible elsewhere in the ocean. Energy moves quietly through this world, not as a single force, but as a continuous exchange, passing from one form of life to another. It begins with the simplest transformations, where light is captured and stored, then carried forward through layers of feeding, growth, and motion. This flow does not rush or falter. It settles into patterns that have been refined over long stretches of time, forming systems that operate with a steady, almost seamless rhythm. At the base of these systems are the primary producers, organisms that draw energy directly from their environment. On land, plants anchor themselves and convert sunlight into the substance that supports all higher life. In the oceans, microscopic life performs a similar role, drifting within the upper layers of water and sustaining entire communities through their presence. These producers do not act in isolation. Their abundance and distribution shape everything that follows, determining where life can gather and how densely it can exist. From this foundation, herbivores take their place, consuming plant material and transforming it into movement, growth, and reproduction. Their bodies become vessels through which energy continues its passage, linking the stillness of plants to the activity of animals. They do not simply feed. They regulate the structure of vegetation, influencing what grows, what spreads, and what recedes over time. Above them, carnivores refine this flow further, drawing energy from other animals. Some focus on smaller prey, maintaining balance within lower levels of the system, while others rise to positions of greater dominance, shaping the behavior and distribution of entire populations. Each interaction carries energy upward, passing it along with each successful hunt, each consumed meal. What defines this period is not merely the presence of these layers, but the balance that exists between them. Energy transfer remains efficient, with relatively little loss at each stage. Populations stabilize within ranges that allow the system to persist without sharp fluctuations. When herbivores increase, predators respond, and when predators become more numerous, the pressure shifts back, maintaining a dynamic equilibrium that rarely breaks. This balance is not static. It adjusts continuously, responding to subtle changes in environment and availability. Yet these adjustments occur within boundaries that have been established over long periods, preventing the system from drifting too far in any one direction. The result is a network of interactions that feels both active and stable, a system in motion that rarely loses its structure. Nutrient cycles reinforce this stability. Organic material returns to the environment through decomposition, feeding the base of the system once more. This recycling ensures that energy does not simply pass through and vanish, but remains part of an ongoing cycle that sustains life across generations. Each level depends on the others, creating a web where no single part exists independently. Across both land and sea, these food chains represent a culmination of evolutionary refinement. Each role has been shaped by countless interactions, each connection tested and adjusted over time. The relationships between species have settled into patterns that support continuity, allowing ecosystems to persist with remarkable consistency. Within this layered structure, life flows with quiet efficiency, guided by connections that have endured through ages. The system holds together not through force, but through balance, each part sustaining the next in a continuous, unbroken exchange. Survival here does not depend on dominance alone, but on restraint, timing, and an ability to withdraw when the surface becomes too demanding. Many creatures shape their lives around avoidance rather than confrontation, finding ways to endure conditions that press steadily against their limits. Their strategies are not always visible, yet they define how life persists across a landscape that rarely offers comfort. Beneath the ground, a quieter world takes form. Burrowing becomes one of the most effective responses to surface extremes, allowing animals to move into layers of soil where temperature shifts are less severe. These underground spaces hold a steadier climate, protecting against the intensity above. Tunnels extend just deep enough to retain moisture and reduce exposure, creating refuges where energy can be conserved and vital processes can continue without interruption. Some species construct simple burrows, little more than shallow depressions that provide temporary relief. Others develop more complex systems with branching passages that offer multiple points of entry and exit. Within these spaces, animals rest, digest, and wait. The act of retreat becomes part of their rhythm, a regular movement between surface and shelter that aligns with the changing conditions of their environment. Activity often shifts toward the darker hours. As light fades and temperatures ease, movement increases. Nocturnal patterns emerge, not as a preference, but as a necessity shaped by the demands of heat and dryness. Under reduced light, animals travel, feed, and interact with greater freedom, their bodies operating within a range that allows for sustained effort. The night becomes a time of quiet motion, where the landscape, though dim, offers a more stable setting. Water, always limited, shapes behavior in equally subtle ways. Conservation becomes essential, influencing both physiology and habit. Some animals develop skin that reduces moisture loss, forming a barrier that slows evaporation. Others produce concentrated waste, retaining as much water as possible within their bodies. These internal adjustments allow them to function with less reliance on external sources, extending the time they can endure between opportunities to replenish. Feeding strategies also adapt to this constraint. Rather than consuming large amounts of water-rich material, some species rely on metabolic processes that generate water internally, extracting what they need from the breakdown of food. This efficiency reduces dependence on scarce resources, allowing life to continue even when conditions remain dry for extended periods. Protection from the environment appears in physical form as well. Thick skin, scales, or armored surfaces provide defense not only against predators, but against the elements themselves. These coverings reduce water loss, shield against abrasive conditions, and offer a degree of insulation from temperature fluctuations. Their presence reflects a dual purpose, serving both survival and resilience in a setting where exposure carries constant risk. These strategies do not operate in isolation. They combine, overlap, and adjust, forming a network of responses that allow organisms to persist within narrow margins. A creature may burrow during the day, emerge at night, conserve water through its physiology, and carry protective coverings, each trait reinforcing the others. In this world, survival is not defined by a single adaptation, but by the integration of many, each contributing to a balance that must be maintained continuously. Life endures not by overcoming the environment, but by moving with it, adjusting in quiet, deliberate ways that allow it to remain within the limits that the world provides. Across the open stretches and clustered habitats, movement is rarely without consequence. Paths intersect, trails overlap, and the presence of one creature quietly influences the decisions of another. In this world, space is not empty. It is claimed, tested, and sometimes defended, shaped by the needs of those who depend on it. Predators do not roam without awareness of each other. Their existence is tied to the availability of prey, and that resource, though sufficient to sustain the system, is never without limits. Where prey gathers, predators follow, and where multiple hunters converge, a subtle tension begins to form. This is not always expressed through direct conflict, but through spacing, timing, and avoidance, each individual adjusting its movements to reduce unnecessary risk. Territorial behavior likely emerges as a natural response to these pressures. Certain areas offer more reliable access to food, shelter, or favorable conditions, and these zones become loosely defined regions of influence. A predator may return to the same ground repeatedly, learning its patterns, tracking the movements of prey, and recognizing the signs left by others of its kind. These repeated movements create boundaries that are not marked by visible lines, but by familiarity and memory. Encounters between rivals do occur, though they are often brief and measured. Displays of presence, posture, or movement may be enough to establish dominance without the need for prolonged struggle. Physical confrontation carries risk, and even a small injury can have lasting consequences in an environment where survival depends on continued efficiency. As a result, many interactions resolve through recognition rather than force, maintaining distance while preserving strength. For prey species, this dynamic introduces another layer of complexity. They move within landscapes where multiple predators may overlap, each with its own patterns and strategies. Their survival depends on reading these patterns, adjusting their behavior to avoid areas of higher risk, and responding quickly when danger approaches. In doing so, they influence the distribution of predators themselves, creating a feedback loop that shapes the movement of both hunter and hunted. Scarcity, even when not extreme, plays a defining role in this system. Resources do not need to vanish entirely to create pressure. A slight reduction in available prey, a shift in distribution, or a seasonal change can alter the balance, increasing competition and forcing adjustments. These pressures do not act suddenly, but build gradually, guiding evolutionary changes over time. Traits that support efficiency, awareness, and adaptability become more prominent. Predators refine their hunting strategies, conserving energy and improving success rates. Prey species develop heightened sensitivity to their surroundings, improving their ability to detect and respond to threats. These changes accumulate, shaping populations in ways that reflect the ongoing interplay between availability and demand. Despite these pressures, the system maintains a form of equilibrium. Populations rise and fall within ranges that allow the broader network to continue functioning. No single species overwhelms the others, and no resource is depleted beyond recovery. This balance, however, remains delicate, dependent on the continued alignment of many factors. In this quiet negotiation of space and survival, competition does not break the system. It defines it, holding each part within limits that allow the whole to endure. New life begins quietly, often concealed within thin layers of protection that separate it from the surrounding world. Eggs rest in sheltered spaces, placed with care in soil, vegetation, or near water, each one holding the early stages of development within a fragile boundary. This method of reproduction dominates across much of the land, a strategy that allows life to continue without the need for prolonged parental presence, yet one that carries its own risks. The shell or outer covering offers only limited defense. It guards against minor disturbances and helps regulate moisture, but it cannot fully shield what lies inside from the broader conditions of the environment. Temperature, humidity, and exposure all influence the outcome. If the surrounding conditions remain within a suitable range, development proceeds steadily. If they shift too far, the process may slow, halt, or fail entirely. Placement becomes a critical decision. Many species select locations that provide a degree of stability, areas where the ground retains some moisture or where cover reduces direct exposure. These choices are shaped by instinct, refined over generations, yet they cannot guarantee success. The environment itself remains variable, and what serves as a suitable site in one period may become less reliable in another. Once the young emerge, their vulnerability becomes immediately apparent. They enter a world where size offers little protection and experience is absent. Movement is often limited, and the ability to respond to threats is still developing. Predators, attuned to these opportunities, may focus their attention on these early stages, where the effort required to secure a meal is reduced. Climate adds another layer of challenge. Conditions that adults have adapted to endure can still place significant strain on the young. Heat, dryness, and fluctuations in temperature affect their ability to regulate internal processes. Access to water or suitable shelter becomes essential, yet these resources may not always be within reach. Survival depends on finding balance quickly, adjusting to the environment within a narrow window of time. As a result, survival rates remain low. Many individuals do not reach maturity, their lives ending before they can contribute to the next generation. This outcome is not an exception, but a consistent aspect of the system. Populations persist not because every individual survives, but because enough do. The number of offspring produced helps offset these losses, maintaining continuity even when conditions are demanding. This balance between reproduction and survival shapes the structure of populations. When conditions allow for greater success among the young, numbers may increase, placing additional pressure on resources. When survival declines, populations may contract, easing that pressure. These fluctuations occur within limits, guided by the availability of food, space, and suitable conditions. Parental involvement varies, often limited in duration or absent after the initial placement of eggs. This approach reflects the broader environment, where extended care may not always be possible. Instead, the strategy relies on numbers and timing, ensuring that at least some individuals reach maturity despite the challenges they face. Through this process, life continues in a steady rhythm, shaped by both vulnerability and resilience. Each generation emerges under conditions that test its ability to endure, and those that succeed carry forward the patterns that allow the system to persist. The changes begin quietly, almost imperceptible within the broader continuity of the world. Nothing dramatic interrupts the flow at first, no sudden break in the patterns that have persisted for so long. Instead, the signs appear as slight deviations, small shifts that ripple through ecosystems without immediately drawing attention. In certain regions, the record left behind in layers of sediment reveals a gradual thinning of life. Species that once appeared consistently begin to show gaps, their presence less frequent, their numbers reduced. These absences are not abrupt enough to signal collapse, but they mark a change in continuity, a quiet reduction that suggests underlying pressures beginning to take hold. Communities that once held a wide range of forms start to simplify. Diversity decreases, not everywhere at once, but in scattered areas where conditions begin to favor fewer species. Some organisms persist, continuing to occupy their roles, while others fade, unable to maintain their place within shifting circumstances. The result is a subtle narrowing of ecological variety, a system that still functions, yet with fewer participants. These changes extend into the relationships that connect different levels of life. Food chains, once stable and well layered, begin to show small disruptions. Certain links weaken as populations decline, altering the flow of energy through the system. Predators may encounter fewer prey, while herbivores may find their food sources less reliable. These adjustments do not cause immediate failure, but they introduce a new uncertainty into interactions that had once remained steady. The effects move gradually, carried through time rather than appearing all at once. A decline in one group influences another, which in turn affects others still, creating a chain of responses that spreads across the landscape and into the oceans. Each change remains small in isolation, yet together they form a pattern that begins to shift the balance. Environmental conditions may also play a role in these early signals. Subtle variations in temperature, moisture, or atmospheric composition influence the distribution and success of species. These factors do not yet reach extremes, but they begin to alter the boundaries within which life operates. Some organisms adjust, finding ways to persist, while others struggle to maintain their position. Despite these developments, the overall system continues to function. Life remains widespread, interactions still occur, and ecosystems retain their structure. The changes, though present, do not yet disrupt the broader continuity. They exist beneath the surface, detectable only through careful observation, leaving the outward appearance of stability largely intact. In this stage, the world does not yet reveal the scale of what is beginning to unfold. The signs are too subtle, too gradual, to be recognized as part of a larger transformation. They appear as isolated shifts, variations that might be expected within any long span of time. Yet within these small adjustments lies the beginning of something more significant. The balance that has been maintained over ages starts to loosen, not through sudden force, but through a series of quiet alterations that slowly reshape the system. The world continues, still steady, still functioning, though no longer entirely unchanged. Far to the north, beneath a region that would one day be known as Siberia, the ground begins to change in ways that are not yet visible at the surface. Deep within the crust, pressure builds slowly, driven by forces that have been gathering over immense spans of time. Heat accumulates, rock softens, and molten material finds pathways upward, seeking release through fractures that widen with each passing moment. At first, these changes remain hidden. The surface shows little sign of what lies below, and life continues its quiet patterns above. Yet, beneath this apparent stillness, a vast system is forming, one capable of reshaping the land on a scale rarely seen. When the first openings reach the surface, the transformation begins, not as a single eruption, but as a prolonged outpouring that extends across large regions. Lava emerges and spreads outward in thick, flowing sheets, covering the ground with a new layer that hardens as it cools. These flows do not remain confined to small areas. They extend across wide distances, filling low-lying regions and altering the contours of the land. Over time, successive flows build upon one another, creating vast expanses of solidified rock that stretch far beyond the point of origin. The process continues in cycles, each phase adding to the accumulation. What begins as isolated outpourings becomes a sustained event, with repeated releases of molten material reshaping the surface again and again. The land transforms gradually, not through sudden peaks of activity, but through persistence, each layer contributing to a growing expanse that alters the environment. Alongside the movement of lava, gases are released into the atmosphere. These emissions include large quantities of carbon dioxide, along with other compounds that rise and disperse through the air. Though invisible, their presence begins to influence the broader system, contributing to changes that extend far beyond the regions of active volcanism. The scale of this activity becomes immense. It is not a single eruption or a brief period of change, but one of the largest volcanic events in Earth's history, unfolding over extended time. The volume of material released, both molten and gaseous, reaches levels that have the potential to alter global conditions. What begins beneath the surface now extends into the atmosphere and across the land, connecting distant parts of the world through its effects. As lava flows continue, they cover existing ecosystems, replacing them with new terrain that must cool and settle before life can return. The transformation is not immediate in its consequences, but it introduces a steady pressure, altering habitats and the conditions upon which life depends. The ground itself becomes part of the change, no longer stable in the way it once was. The gases released into the atmosphere begin to accumulate, contributing to shifts in temperature and composition. These changes unfold gradually, carried by atmospheric circulation to regions far from their source. The effects are subtle at first, blending into the existing patterns of climate, yet they begin to add weight to the system, nudging it toward new conditions. In this unfolding process, the forces beneath the surface reveal their reach. What begins deep within the earth emerges slowly, reshaping both land and air through a series of connected changes. The scale of this activity extends beyond any single region, becoming part of a broader transformation that continues to build with each passing phase. The sky begins to change in ways that leave no visible boundary, yet touch every surface below. Its composition shifts gradually, carried by currents that move unseen across the planet, blending gases into a mixture that no longer holds the same balance as before. The alteration is subtle at first, woven into the air that surrounds every organism, yet its effects begin to accumulate with quiet persistence. Carbon dioxide rises within this shifting atmosphere, its presence increasing as volcanic emissions continue to enter the air. This gas, though invisible and without immediate sensation, holds heat in ways that begin to influence the global system. Sunlight reaches the surface and is absorbed, then released again, yet more of that energy remains trapped, held within the lower layers of the atmosphere rather than dispersing into space. As this process continues, global temperatures begin to climb. The warmth that already defines much of the world deepens, extending further into regions that once held a narrower range of conditions. The difference is not always dramatic in a single moment, but it builds over time, adding to the cumulative effect of each passing cycle. Heat lingers longer, settles more firmly, and alters the patterns that living systems depend upon. Alongside this warming, oxygen levels begin to fluctuate. The balance between production and consumption shifts as ecosystems respond to changing conditions. Some environments may produce less oxygen, while others consume it more rapidly, leading to variations that affect how organisms sustain their internal processes. Breathing, once a steady exchange, becomes slightly more demanding, particularly in regions where these changes are more pronounced. For life on land, these atmospheric shifts introduce new pressures. Increased temperatures influence behavior, forcing adjustments in activity patterns and habitat use. Water loss may accelerate, placing additional strain on organisms that already operate within narrow margins. Even small changes in oxygen availability can affect endurance, limiting the duration and intensity of movement. In marine environments, the effects extend through the water itself. As the atmosphere warms, so too do the upper layers of the ocean, altering the distribution of dissolved gases. Oxygen becomes less available in warmer water, creating conditions that challenge organisms dependent on it. Subtle imbalances begin to form, influencing where species can survive and how they interact within their environment. The changes do not occur in isolation. Rising carbon dioxide, increasing temperatures, and shifting oxygen levels combine, each reinforcing the others in a system that grows more complex with time. What might seem minor on its own becomes significant when linked together, creating conditions that gradually move beyond the ranges to which life has adapted. Despite these developments, the world continues to function. Ecosystems adjust, species respond, and life persists within the changing atmosphere. Yet the stability that once defined these systems begins to loosen, not through sudden disruption, but through a steady accumulation of stress. The air, once a quiet constant, becomes an active participant in the transformation, shaping conditions across both land and sea through changes that are subtle, continuous, and far-reaching. Beneath the surface, where light fades and distance softens into a slow, drifting quiet, the first changes take hold without sound. The ocean, long shaped by steady exchange and layered motion, begins to shift in ways that are not immediately visible, yet carry deep consequences for everything that depends on it. As temperatures rise, the upper waters grow warmer, altering the delicate balance that governs the movement of oxygen through the sea. Warmer water holds less dissolved oxygen, reducing the amount available to organisms that rely on it for respiration. This change is gradual, almost unnoticeable in a single moment, yet it spreads across wide regions, subtly lowering the baseline upon which marine life depends. At the same time, the structure of the ocean begins to adjust. Differences in temperature between surface and deeper layers become more pronounced, creating a barrier that slows the natural mixing of water. Normally, currents and shifts in density allow oxygen-rich surface water to circulate downward, replenishing deeper zones. As this process weakens, the layers begin to separate more distinctly, limiting the flow that once connected them. In the deeper regions, this reduced mixing leads to stagnation. Water that is no longer regularly refreshed begins to lose oxygen over time, consumed by organisms and decomposition without sufficient replacement. These zones become increasingly depleted, forming areas where life must either adapt, move away, or gradually decline. The change does not arrive as a sudden absence, but as a steady reduction that narrows the conditions in which survival remains possible. Marine life responds in quiet ways. Some species shift their range, moving toward areas where oxygen remains more accessible. Others reduce activity, conserving energy in response to the diminished availability of what they require. For many, these adjustments provide temporary stability, yet they also compress populations into smaller regions, increasing competition and altering long-established patterns of interaction. Organisms that cannot relocate or adapt quickly enough begin to experience greater stress. Growth slows, reproduction becomes less successful, and mortality rates increase. These effects accumulate over time, gradually reshaping communities that once thrived under more stable conditions. The structure of marine ecosystems begins to shift, not through visible collapse, but through the steady weakening of its components. The earliest signs of disruption appear in these deeper layers, far from the surface where observation would be easier. Here, in the dim regions where movement is already slower and life more dispersed, the loss of oxygen alters the foundation upon which entire systems rest. What occurs in these hidden zones does not remain isolated. It begins to influence the layers above, affecting the distribution and behavior of species throughout the water column. Currents continue to move, and the surface may still appear active and unchanged. Yet beneath this activity, the underlying system is adjusting in ways that are not immediately apparent. The ocean, once defined by its continuity, begins to carry subtle divisions, its layers less connected than before. These changes unfold without urgency, without sudden breaks, yet their reach extends across vast distances. The transformation begins where it is hardest to detect, in places where light does not reach and movement is slow, setting into motion a process that quietly alters the balance of life within the sea. Within the quiet chemistry of the ocean, a gradual shift begins, one that alters the very substance of the water itself. Carbon dioxide, already rising in the atmosphere, dissolves into the sea in increasing amounts, becoming part of the fluid that surrounds every marine organism. This process unfolds without sound or visible boundary, yet it changes the balance of compounds that define the ocean's internal structure. As carbon dioxide enters the water, it reacts to form carbonic acid, a transformation that lowers the pH of the surrounding environment. The change is slight at first, a subtle increase in acidity that spreads through surface waters and begins to extend downward. Over time, this adjustment accumulates, reshaping the conditions under which many organisms have evolved. For those that build shells or skeletal structures from calcium compounds, the shift presents a particular challenge. The materials they rely on become less stable in more acidic conditions, making it harder to form and maintain their protective layers. Brachiopods, along with other shell-forming creatures, begin to experience difficulty in constructing the structures that define their existence. Growth slows, shells thin, and the effort required to maintain them increases. Reef systems, already sensitive to environmental changes, begin to respond to this altered chemistry. The organisms that contribute to their framework find it more difficult to deposit the minerals needed to sustain their structures. Over time, this affects the integrity of the reef itself. Growth diminishes, and areas that once expanded begin to weaken. The intricate architecture that supports so many forms of life starts to lose its stability. These changes ripple outward, affecting not only the organisms directly involved, but the many species that depend on them. As reef structures decline, the spaces they provide become less secure. Sheltered areas shrink, and the complex network of interactions that once thrived within them begins to simplify. Species that relied on these environments for feeding, reproduction, or protection must adjust or relocate, altering the composition of entire communities. The effects extend further into the food chains that connect different levels of marine life. When shell-forming organisms struggle, the organisms that feed on them encounter reduced availability. This change moves upward, influencing predators and the broader distribution of energy within the system. What was once a steady flow begins to show signs of disruption, as each level responds to the weakening below. Acidification does not act alone. It combines with other changes already underway, reinforcing shifts in temperature and oxygen availability. Together, these factors create a more complex environment, one in which stability becomes harder to maintain. Organisms must navigate multiple pressures at once, each influencing their ability to survive and reproduce. Despite these developments, the ocean does not transform suddenly. The process unfolds gradually, its effects building over time. Life continues, adapting where possible, persisting within narrowing ranges of suitable conditions. Yet beneath this continuity, the structure of the system begins to change, its balance becoming less secure. In the chemistry of the sea, a quiet transformation takes hold, one that alters the foundation upon which marine life depends, reshaping interactions in ways that extend far beyond the smallest scales. At a certain point, the gradual shifts no longer remain contained within quiet adjustments. The balance that once held the ocean together begins to give way, not in a single moment, but through a widening pattern of loss that spreads across its depths. What had been a system of continuous exchange starts to unravel, each change reinforcing the next until the structure itself begins to fail. Marine species that once thrived in layered communities begin to disappear in increasing numbers. Some vanish from shallow regions where conditions had already begun to shift, while others fade from deeper waters where oxygen has grown scarce. The losses are not uniform, yet they accumulate across different environments, creating gaps in ecosystems that had once been tightly connected. As these die-offs continue, the scale becomes immense. Up to 90% of marine life is lost, a reduction that reshapes the ocean in ways that extend far beyond individual species. Entire groups that had persisted for long stretches of time decline rapidly, their presence reduced to scattered remnants or removed entirely from the system. The continuity that once defined the marine world breaks into fragments. With the disappearance of so many organisms, ecological networks begin to collapse. Relationships that once connected producers, consumers, and predators no longer function as they had. The flow of energy, once steady and efficient, becomes disrupted, leaving some levels without support while others lose their role entirely. Food chains unravel, their links severed, as key species vanish. Reef systems, already weakened, lose their structural integrity as the organisms that maintain them decline further. Without continuous growth and repair, these frameworks begin to erode, removing the shelter and complexity that supported a wide range of life. As these structures fade, the diversity they once sustained diminishes with them, further accelerating the loss of species. The ocean itself becomes a more difficult environment in which to survive. Oxygen-depleted zones expand, limiting the areas where life can persist. Water chemistry continues to shift, placing additional strain on organisms already weakened by earlier changes. Temperature remains elevated, altering the distribution of species and reducing the stability of habitats that once supported consistent populations. In these conditions, survival becomes increasingly uncertain. Some organisms attempt to adapt, shifting their behavior or moving to regions where conditions remain more favorable. Others cannot respond quickly enough, their decline contributing to the broader pattern of loss. The system, once defined by balance, now carries a growing instability that affects every level. The changes extend across vast distances, connecting shallow and deep regions, coastal areas, and open water. What occurs in one part of the ocean influences another, creating a network of effects that spreads through currents and interactions. The collapse is not confined to isolated zones, but becomes a global event, reshaping the marine world as a whole. In the aftermath of these losses, the ocean no longer holds the same continuity it once did. Its ecosystems, once layered and interconnected, are reduced to simpler forms, with fewer species and diminished interactions. The environment itself becomes less hospitable, its conditions more challenging, and its stability less certain. The transformation unfolds without a single defining moment, yet its scale becomes undeniable, leaving behind an ocean profoundly altered from what it had been. Across the land, the changes arrive not as a single event, but as a quiet thinning that moves through living systems with increasing speed. What once held together through steady exchange begins to loosen as the foundation beneath it starts to shift. The first signs appear in the vegetation, where growth becomes less reliable and distribution more uneven, altering the availability of the energy that sustains all higher forms of life. Plants that once formed the base of terrestrial systems begin to decline in certain regions, their presence reduced by shifting conditions that no longer support consistent growth. Some areas experience diminished regeneration, while others lose entire communities that had once persisted there. The effect is not uniform, yet it spreads, creating gaps where food had once been dependable. Herbivores respond quickly to these changes, their survival closely tied to the availability of plant material. As food sources diminish, their populations begin to contract. Movement patterns shift as they search for remaining resources, often traveling farther or concentrating in areas where vegetation still persists. This increased pressure on limited resources accelerates the decline as overuse prevents recovery and further reduces availability. The loss of herbivores carries immediate consequences for the predators that depend on them. As prey becomes scarce, hunting becomes less successful, requiring greater effort for diminishing returns. Predators may expand their range, seeking new areas where prey might still be found, yet these movements often bring them into competition with others facing the same conditions. The balance that once supported their dominance begins to erode. Without sufficient prey, predators face a gradual weakening. Energy reserves diminish, reproduction declines, and survival becomes increasingly uncertain. Some individuals may persist longer through efficiency or adaptability, but many cannot maintain their position within the system. The absence of reliable food sources reshapes their role, reducing their numbers and altering their influence on the environment. As these changes unfold, the structure of terrestrial ecosystems begins to unravel. The connections that once linked plants, herbivores, and predators weaken, each level affecting the others in a cascading pattern. What had been a layered system of interactions becomes fragmented, with fewer species and diminished relationships holding it together. The pace of this transformation is more rapid than the earlier shifts that preceded it. Once the foundation begins to fail, the effects move quickly through the system, leaving little time for gradual adjustment. Areas that once supported diverse communities become simpler, their complexity reduced as species disappear or relocate. Despite this, the land does not fall silent all at once. Life persists in scattered forms, adapting where possible, seeking out remaining resources, and continuing within the narrowing conditions that remain. Yet the overall pattern reflects a clear movement away from stability, toward a state where the system can no longer sustain its previous structure. In this unfolding process, the decline of one group leads directly to the weakening of another, creating a chain of effects that spreads across the landscape. The loss of food sources initiates a sequence that reaches every level, altering the balance that once allowed life to exist in a steady, interconnected way. The land, like the sea before it, begins to change in ways that reshape the very framework of its ecosystems. At the highest levels of the food web, where strength and precision once secured a stable position, a quiet unraveling begins to take hold. The creatures that had long occupied these upper tiers now move through a world that no longer supports the balance upon which their dominance depended. Their abilities remain unchanged, yet the conditions around them shift in ways that those abilities cannot overcome. Predators rely on a steady presence of prey, a connection that has guided their evolution over countless generations. As those prey populations decline, the foundation beneath these hunters weakens. Encounters become less frequent, and the effort required to secure each meal increases. What was once a reliable pattern begins to fragment, leaving gaps where sustenance had once been found. Among these predators, the gorgonopsians, once refined and efficient hunters, face the same quiet pressures. Their speed, their precision, and their specialized teeth remain, yet these traits depend on a system that is no longer intact. Movement through their territory yields fewer opportunities, and each hunt carries greater uncertainty. The landscape they navigate still exists, but the network of life that supported them has begun to fade. As energy becomes harder to obtain, the effects extend inward. Strength diminishes gradually, not through sudden failure, but through a slow reduction in the resources needed to maintain it. Reproduction declines. As individuals lack the surplus energy required to sustain new life, populations begin to contract, their numbers decreasing with each passing cycle. Dominance, once a defining advantage, offers no protection in this changing environment. The traits that allowed these predators to rise to the top of their ecosystems were shaped within a stable system, one that provided consistent access to prey and predictable interactions. When that system breaks down, those same traits become less effective, unable to compensate for the absence of what they depend upon. Other top predators experience similar patterns. Each, in its own way, faces the same fundamental challenge, a reduction in the flow of energy that once supported its position. Competition may intensify as remaining prey becomes scarce, yet this does not restore balance. Instead, it adds further strain, accelerating the decline. The disappearance of these predators does not occur in a single moment. It unfolds gradually, their presence becoming less frequent until it fades entirely from certain regions. Fossil records later reveal these absences, marking the end of lineages that had once defined their environments. With their decline, the structure of the ecosystem shifts further. The absence of apex predators alters the behavior of remaining species, yet this change does not restore stability. The system, already weakened, continues to move away from the balance it once held. In this process, the fall of the most powerful hunters becomes a clear sign of the broader transformation. Their disappearance reflects not a failure of their own design, but the collapse of the system that sustained them. Strength, speed, and efficiency remain, yet without the conditions that supported them, these qualities cannot ensure survival. The highest levels of the food web, once defined by control and precision, grow quieter, their defining figures gradually disappearing into the shifting landscape. Sound begins to withdraw from the world, not all at once, but in a gradual softening that spreads across land and water alike. Where movement once carried with it a constant background of life, the rhythms begin to slow, and the spaces between them grow wider. The landscape remains, yet something essential within it is fading, leaving behind a stillness that was not present before. Forests, once scattered but steady, begin to thin further. Trees that had endured long cycles of growth now stand more sparsely, their regeneration uncertain as conditions no longer support consistent renewal. Some regions lose their vegetation entirely, leaving open ground where roots no longer hold the soil. The layered structure that once supported countless forms of life diminishes, and with it, the subtle activity that filled those spaces. Without the stabilizing presence of plant life, the land begins to change in texture and form. Soil becomes more exposed, more prone to shifting under wind or the occasional flow of water. Areas that once provided shelter and resources now offer little to sustain the organisms that remain. Movement across these regions becomes more difficult, not because of obstacles, but because of absence. Water sources, already altered, continue to decline. Rivers shrink or break into disconnected segments, their flow reduced by changing conditions. In some places, what remains carries compounds that alter its quality, making it less suitable for sustaining life. The edges where animals once gathered become less active, their significance fading as the reliability of water diminishes. As these changes progress, the presence of animals becomes less apparent. Large herbivores that once shaped the land through their movement are no longer seen in the same numbers. Predators, already reduced, leave fewer traces behind. Smaller creatures persist in scattered forms, yet their activity does not fill the spaces left behind by those that have vanished. The sounds that once accompanied these movements begin to fade. Footsteps, feeding, calls, and the subtle interactions between species grow less frequent. The environment, though still capable of producing sound through wind or shifting ground, loses the layered complexity that living systems once contributed. What remains is a quieter version of the world, where activity continues but at a diminished scale. This silence does not arrive as a single moment, but as an accumulation of absences. Each missing species, each reduced population, contributes to a broader quieting that spreads across the landscape. The change is not defined by what is added, but by what is no longer present. Even as life persists in limited forms, the overall character of the planet shifts. The connections that once linked different systems weaken, and the interactions that sustain them become less frequent. What remains is a world that continues to exist, yet no longer carries the same vitality. In this stillness, the transformation becomes clear, not through dramatic events, but through the gradual disappearance of the sounds and movements that once defined the living earth. In the aftermath of widespread loss, what remains is not empty, but reduced to quieter forms that persist within narrow margins. Life does not disappear entirely. Instead, it contracts, leaving behind those that can endure conditions that have become increasingly difficult. These survivors are not defined by dominance or size, but by adaptability, by the ability to function within a world that no longer supports complexity in the way it once did. Many of these enduring species are small, their scale allowing them to require fewer resources and to respond more quickly to changes in their surroundings. Their needs are modest, their movements less demanding, and their presence easier to sustain in environments where food and water have become uncertain. Size, which once offered advantages, now yields to efficiency, favoring those that can persist with less. Burrowing animals find themselves in a position of relative stability. Beneath the surface, conditions remain more consistent, shielded from the extremes above. These underground spaces provide protection not only from temperature fluctuations, but also from the broader environmental shifts that continue to reshape the surface. Within these sheltered areas, life can continue with fewer disruptions, allowing certain species to maintain their presence while others decline. These animals rely on behaviors that allow them to withdraw when necessary, emerging only when conditions permit. Their existence becomes a cycle of retreat and cautious activity, each movement aligned with the narrow windows in which survival is possible. This pattern, once one of many strategies, now becomes central to persistence. Generalist species also hold an advantage. Those that can consume a wide range of food sources that can adjust their behavior and habitat use find ways to continue where more specialized organisms cannot. Specialists, once finely tuned to specific conditions or diets, face greater difficulty as those conditions change or disappear. The flexibility of generalists allows them to navigate the altered landscape, adapting to what remains rather than depending on what has been lost. Reproduction continues, though often at reduced levels. The survival of offspring remains uncertain, yet enough endure to sustain these populations. Each generation carries forward traits that favor resilience, gradually shaping the characteristics of those that persist. Over time, these qualities become more pronounced, reflecting the demands of the environment. The world that surrounds these survivors is quieter, simpler, yet not entirely without continuity. The connections between organisms still exist, though in reduced form. Energy continues to move through the system, carried by fewer participants, yet still forming the basis for ongoing life. Within these remnants, the potential for future change remains. The species that endure carry within them the capacity to diversify once conditions allow. Their survival preserves the threads from which new ecosystems can eventually emerge, though this process will unfold over long periods of time. These survivors do not restore what has been lost, nor do they recreate the complexity that once defined the world. Instead, they maintain a presence, holding on to existence within a landscape that has been fundamentally altered. Their persistence ensures that life continues, even in its most reduced state. In their quiet endurance, they represent not an end, but a continuation, a subtle foundation upon which the future will slowly take shape. After the long unraveling, the planet settles into a quieter state, one defined less by absence than by simplicity. The structures that once supported intricate networks of life have been reduced, leaving behind a world where connections are fewer and more fragile. Yet within this stillness, the conditions for change remain, subtle and patient, unfolding over spans of time that stretch far beyond immediate perception. Ecosystems, once layered and complex, now exist in simplified forms. Many of the relationships that once linked species together have been lost, and what remains operates on a smaller scale. The flow of energy continues, though it moves through fewer pathways, carried by organisms that have endured the transition. These systems do not resemble what came before, yet they retain the essential processes that allow life to persist. Across both land and sea, spaces that were once occupied now lie open. Niches that supported specific roles within ecosystems remain unfilled, their previous inhabitants gone. These gaps create opportunities, though not immediately. For a time, they exist as quiet possibilities, waiting for conditions and organisms capable of meeting them. In the oceans, the absence of former communities leaves stretches of water where diversity is greatly reduced. The intricate interactions that once defined these environments have given way to simpler arrangements. On land, similar patterns emerge, with fewer species shaping the environment and influencing one another. The overall structure of life becomes less dense, its complexity diminished but not erased. Recovery begins slowly, not as a return to what was, but as a gradual emergence of new patterns. Over millions of years, surviving lineages begin to expand, their populations increasing as conditions stabilize. Variation within these groups leads to the development of new forms, each adapted to the environments that now exist. This process unfolds quietly, generation by generation, without any single moment marking its progress. As these changes accumulate, new interactions begin to form. Organisms that once played minor roles may take on greater significance, while entirely new combinations of traits appear. Evolution explores pathways that had not been available before, shaped by the altered landscape and the absence of previous competitors. The world that develops from this process does not mirror the one that was lost. It follows a different course, guided by the survivors and the conditions that remain. Over time, complexity begins to increase again as new species fill the spaces left behind and establish their own relationships. The rebuilding of ecosystems occurs gradually, each step building upon the last. This transformation is not driven by urgency, but by persistence. Life continues to adapt, to expand, and to diversify, even after such extensive loss. The pace is measured, unfolding over intervals that allow small changes to accumulate into larger shifts. In this renewed world, the foundations of future ecosystems take shape, not as replicas of the past, but as new arrangements that reflect both loss and continuity. The planet moves forward, carrying with it the traces of what endured and the possibilities that arise from what remains. What remains from this distant chapter is not only the record of loss, but a pattern that echoes through the way the planet functions. The events that unfolded across that ancient world reveal how deeply connected its systems were, how changes in one part could move outward, shaping conditions far beyond their origin. The scale of the transformation, the largest extinction event in Earth's history, reflects not a single cause, but a convergence of forces that together altered the balance of the entire planet. The stability that existed before the collapse was not accidental. It was built over immense spans of time through interactions that gradually formed a system capable of sustaining complexity. Climate, atmospheric composition, and biological networks worked together, each influencing the others in a continuous exchange. When one element shifted beyond a certain point, the effects did not remain isolated. They moved through the system, linking changes in air, water, and life into a single unfolding process. This interconnectedness becomes most visible in moments of disruption. Rising gases altered the atmosphere, which in turn influenced temperature and the chemistry of the oceans. These changes affected the organisms that depended on those conditions, and as those organisms declined, the structures they supported began to weaken. Each step followed from the last, creating a sequence in which the system moved further from the balance it once held. The collapse demonstrates that even long-standing stability can be sensitive to sustained pressure. The world of that time had endured previous changes, adapting and continuing, yet the combination of factors it faced proved more difficult to absorb. The result was not a gradual adjustment, but a shift that exceeded the system's ability to maintain itself in its existing form. At the same time, the persistence of life within this transformation reveals another aspect of the planet's nature. Even as ecosystems diminished and many lineages ended, others continued, carrying forward the capacity for future growth. This resilience is not a guarantee of continuity in any particular form, but a reflection of life's ability to adapt within changing conditions. It ensures that while systems may collapse, life itself does not vanish entirely. The distinction between resilience and invincibility becomes clear in this context. Life can endure, but not without change and not without loss. The forms that existed before the collapse did not all persist into what followed. Many were replaced, their roles taken on by new organisms that emerged over time. The continuity lies in the process, not in the preservation of specific structures. Looking back across this immense span, the events of that period remain part of the planet's ongoing story. They illustrate how closely linked its systems are and how shifts in one domain can influence the others in ways that accumulate over time. The world that exists now operates under the same fundamental principles, shaped by the same interactions between atmosphere, climate, and life. In this way, the story extends beyond its place in the past. It reflects the nature of the planet itself, a system capable of both stability and transformation, where even the strongest arrangements depend on a balance that must be maintained.